วัสดีครับ In this chapter we will talk about an important quantity in physics, especially when we talk about the rotation. This quantity is the angular momentum. The angular momentum has a definition which is more or less similar to the linear momentum, and we will see that this angular momentum is closely related to the quantity that we call torque. We talked about this quantity before when we talk about the rotation of the rigid body. Here in this chapter we will define we will discuss the formal definition of the torque, where we represent this definition in terms of the vector product of the cross product of the position vector of a particle and the force that acts on that particle. And then we will define the angular momentum and the relation between the angular momentum and the torque. We will next apply the angular momentum concept to the rotation of the rigid object. Okay. And we will discuss one of the important concepts about the angular momentum, that is, if there is no force or there is no torque applied on an object, the angular momentum will be constant, and that is for the isolated system in the sense that there is no external torque on the object. And finally, we will talk about the gyroscope, which we apply the concept of angular momentum, the relation between the torque and angular momentum, to explain the behavior of the gyroscope and torque. Okay, so let's first go to the first section, the vector product and torque. Firstly, we have to define an operation between two vectors. So far we have defined the operation of two vectors, the algebraic operation and also the dot product of two vectors that give the scalar result. Here we will define the other operation of vector, which we call the cross product, A cross B. By definition, the cross product A cross B will give us the new vector. Here we have C equal to A cross B, and C is a vector. So the cross product we also call it the vector product, because the cross product will give us the vector, or the result of the cross product is a vector. Okay. By definition, the cross product A cross B, which we call C, will have the magnitude C is equal to AB sine theta. This is by definition, where theta is the angle between A and B, as in this figure. And the direction of C will follow what we call the right hand side blue. As in this figure, if we want to find the direction of A cross B, okay, let's first define the direction of A along the forefinger. Okay, so the direction of A is along this direction, and the direction of B point out of the palm like this. This is the palm, like, and B point out of the palm like this. The direction of A cross B, which is the direction of C, will point in the direction of the thumb here. So it's point in this direction. So that is for the direction of A cross B. And the magnitude of A cross B, it follows this definition. Okay. We can see that from this definition, it is obvious that A cross B is not equal to B cross A. In fact, A cross B is equal to the minus of B cross A. This is quite obvious from this figure. A cross B, you can see that A is point along this forefinger and B is point out of the palm. And if you switch the position of A and B, it will point in the opposite direction. So we have that A cross B is equal to the minus of B cross A. That is one identity of the cross product. So we can say that the vector product or the cross product is not commute, or it has no commutative property. We have that A cross B is equal to the minus of B cross A. Okay. And from the definition of the magnitude of A cross B, we have C equal to A B sine theta. So you can see that if theta is 0 or pi, or we can say it's 180 degrees, we have sine theta is 0, so A cross B is 0. This means that if A and B is parallel, if A and B are parallel, or if A is parallel to B. Parallel to B can be both A point in the same direction to B or A point in the opposite direction to B. In both cases, we have A cos B equal to 0. This gives us that if we do the cross product of the vector with itself, we will have 0. Okay. Now, if A is perpendicular to B, so in this case, it means that theta is equal to half of pi, or t pi over 2. In both cases, we will have sine theta is equal to, if theta is pi over 2, we have sine theta equal to 1, and if theta is equal to 3 pi over 2, we have sine theta equal to minus 1. But if we talk about the magnitude, we will put the positive value only. So if A and B is perpendicular to B, okay, we can say that A cross B is equal to AB, because the sine theta equal to 1. Okay. The cross product obeys the distributive law. That is, if we calculate A cross B plus C, we can if U equal to A cross B plus A cross C. We call this a distributive law. To prove this law is not difficult but tedious, so I will put the proof in an separate video which uh, created by someone else, not me, but it's very useful. Okay. And when we do the derivative of the cross product, okay, we have to maintain the order or to preserve the order of the product. For example, we have d by dt of a cross b is equal to the d by dt of a cross b plus a cross d by db by dt. Okay. To prove this property is quite simple. Once we have proved the distributive law, and when we express the cross product in terms of the for example, the rectangular representation. Okay, so we will go on with okay. Sometimes it's simpler if we can express our vector in the rectangular coordinate. Example, if I represent the vector A as AXI plus AYJ plus AZK, and B is BXI plus BYJ plus BZK. And from this representation, we can prove, or we can get the formula to calculate the vector product or cross product quite easily. But first, we have to discuss this identity of cross product first. That is, we have that if we do the cross product of the unit vector I by itself, or j by itself, or k by itself, we will get 0. This is obvious from this identity. Okay, that is, if the vector is parallel, the cross product with itself is 0. Okay, and since I is perpendicular to j and j is perpendicular to k, so we must have some relation between the cross product of I and j and k, and also k and I. This is quite simple and obvious if we draw the unit vector I, j, and k. Okay, for example, if we have the x-axis, y-axis, and z-axis like this. So this is x, y, and z. And we have I, unit vector I, unit vector j, and unit vector k. You can see that it is quite obvious that if we do I cross j, following the right-hand rule, I cross j will point in the direction of k, right? I cross j will point in the direction of k. And we also have that I cross j, the magnitude of I cross j is equal to 1, because the magnitudes of I and j are equal to 1, and the angle between I and j are 90 degrees, or they are perpendicular. So it means that sine theta is equal to 1 in this case. So we have I cross j is equal to k. And if we switch the position of I and j, we must have that I cross j is equal to the minus of j cross I, which is equal to k. Following this step, you can prove easily that j cross k is equal to I, and k cross I is equal to j. So, from these three identities, together with the representation of A and B in the rectangular form, we can prove easily, and I will leave that for the as an exercise, that we can express A cross B in terms of I, J, and K like this. Okay. The process is that we have A cross B is equal to AXI plus AYJ plus AZK cross with the BXI plus BYJ plus BZK. Okay, and you use the distributive law, that is, you may do the cross product of A with the BI first, and then use the distributive law again by do the cross product of BI with the AXI, AYJ, and AZK, and repeat this process for each component of B, and finally we will get this relation. I will leave this as an exercise too, because it's quite straightforward. You can do this by not difficult arithmetic work. Okay, but from this form of A cos B in the rectangular coordinate, we can write down this in terms of determinant. Okay, so we have the compact form of A cross B. You can say that A cross B is equal to the determinant of I, J, K, AX, AY, AC, and BX, BY, BC, like this. And if we resolve this into the T component, we have that AYBC, which is give the positive value, and ACBY, which gives the negative value. Okay, and also the second and the third term, you can do it by yourself. Okay, also you can see that from this representation of A cross B, you can get the derivative of A cross B is equal to the derivative of A cross B plus the A cross the derivative of B. This is quite simple and straightforward if you do the derivative of this expression. Okay, and you will get this relation, and I will leave this as an exercise too. This is quite simple and this is quite obvious. Okay, because when you do the derivative of A cos B, it means that you have to do the derivative of each component, right? And in each component you have the product of A and B. So when you do the derivative of the product, it means that you have to split by doing the derivative of A first, multiply by B, and then derivative of and then multiply A with the derivative of B. Okay, and again when you do the derivative of all terms, you can put it back in the compact vector form to get these term. So it is quite a little bit tedious, but quite simple and quite straightforward. Okay. Now, when we have the definition of the cross product, we will go back to the physics. That is, some physical quantity can be defined as a vector product or cross product. And in this chapter, we will focus on the physical property that called torque. Okay. By definition, we will define the torque of the force F acting on a particle, this one, allow the point O. By this definition, torque is equal to R cross F. Here, R is the position vector point from O to the position of the particle. Okay, to the position of the particle like this. Okay, so we define that torque is equal to R cross F. The direction of the torque follow the right-hand rule. So you can see that if the particle is here, the force F is applied to this particle, and the position vector is R like this. We have torque point in the positive C direction like in this figure. Okay, this is a vector definition of torque, and we will see that this definition is quite useful when we try to relate this quantity torque to what we will define later, the angular momentum.